The world of AI is moving so fast, especially in reinforcement learning. That's basically how we teach machines through trial and error. But the field has gotten so packed with new ideas that it's kind of created this paradox of choice for researchers. So today, we're diving into a new paper that just cuts right through all that noise, offering this single, really elegant idea that unifies a whole bunch of different methods. So, to really get why this is such a big deal, let's try to put ourselves in an AI's shoes for a second. Imagine you're a robot and you're learning to walk. You are just getting flooded with this constant stream of data: camera pixels, joint angles, velocity readings, everything. So, how in the world do you figure out which tiny little fraction of that information is actually important for just taking the next step without falling flat on your face? And that right there, that's a central challenge in modern AI. Information overload. It's a problem researchers call the curse of dimensionality. And honestly, it's a huge reason why an AI's learning process can be so inefficient and sometimes surprisingly brittle. Okay, so here's the bottom line. On one side, you've got what the AI actually sees, this massive, high-dimensional flood of raw data. It is messy, it's noisy, and let's be real, most of it is totally irrelevant. But on the other side is what it needs to know: a tiny, compressed summary that has only the essential info to make the best possible decision. The entire game is about bridging that gap. And, in trying to bridge this gap, researchers have come up with tons of potential solutions. So many, in fact, that the paper points out has created a real paradox of choice. If you're an engineer building one of these systems, you're looking at dozens of options, making it almost impossible to know which tool is even the right one for the job. So all this confusion, it kicked off this big search for the perfect summary, or what researchers would call a representation. The goal was to find a single, reliable way to filter out all that noise and just give the AI exactly what it needs and nothing more. And this search led to a few, let's call them competing theories. Maybe, as the trophy icon suggests, you only need to keep info that helps you get future rewards. Or maybe, like the eye icon, you should focus on predicting exactly what you're going to see in the very next moment. But then there's this third, more abstract idea. What if the only thing you needed to predict was your next summary? And this is where things get really interesting. This brings us to the climax of the paper's argument, the secret that's been hiding inside that third idea all along: the secret of self-prediction. The core concept is called a self-predictive abstraction, and it's actually brilliantly simple. It says that a good summary of the world is one that allows you to predict, well, your next summary. Think about it like this. Instead of trying to predict the entire stock market, you just try to predict what your summary of the market will look like tomorrow. You don't need to predict rewards or raw data, just how your own internal understanding evolves. And here it is, the big aha moment. The paper shows that those different approaches we just looked at, they aren't really competing at all. Turns out they're all deeply connected. By focusing on self-prediction, you can actually derive the properties of the other methods. They're just different sides of the same coin. And this leads to a really powerful conclusion, which the authors actually prove mathematically. If you simply teach an agent to get good at predicting its next internal summary, it automatically learns to predict future rewards, basically as a side effect. This is huge because it means you can learn everything in one simple step without needing some complicated multi-stage training process. So look, this unified theory sounds great on paper, but does it actually work in the real world? To find out, the researchers created this stripped-down minimalist algorithm just to put the whole idea to the test. And the algorithm they came up with is incredibly simple. You just take any standard reinforcement learning agent and you add one simple extra task. While you're learning your main goal, also try to predict what your own summary is going to be in the next time step. That's it. Seriously. No complex reward models, no planning, none of that. So how did it do? Well, on standard benchmarks, this minimalist approach, that's the one on the left, minimalist file, it performs just as well as, and sometimes even better than, a much more complex state-of-the-art model. And as you can see, it just blows the simpler baseline right out of the water. But the real magic, the real test, happens in noisy, distracting environments. Because the self-predictive agent doesn't waste resources trying to predict irrelevant details. It only has to predict its own internal summary. It stays far more robust. I mean, look at that. Its performance barely drops, while the other methods just crumble under the pressure. And
Because the algorithm is so much simpler, you get this massive practical benefit. The researchers found it trains up to 50% faster than the more complex model it was up against. So it's simpler, more robust, and faster. That's a pretty great combo.
Now, I should mention there is one crucial little trick to making all this work. Without it, the AI can get lazy and learn a useless shortcut, like just predicting its summary will always be 0. So a technique called stop gradients is used to prevent this, basically forcing the AI to maintain a rich, dynamic understanding of the world instead of just collapsing into some simple, unhelpful state. So, what's the big takeaway from all of this? Well, when it comes to building the next generation of AI, the paper's conclusion is pretty clear. We might be able to build smarter AI by following much simpler rules.
And they even offer a practical guide for people building these things. First, analyze your task. Self-prediction is great for noisy environments, but other methods might actually be better if your rewards are super rare. Second, they say you should always start with this minimalist algorithm as a baseline. It's simple, it's strong, and it's cheap to run. And they even give specific implementation tips to get you started on the right foot. And all of this leaves us with a final, really fascinating question. For decades, the assumption has kind of been that more powerful AI requires more complex models. But this work suggests that, well, maybe the opposite is true. Maybe the real path to more general and robust intelligence doesn't lie in adding more and more complexity, but in finding these simple, elegant principles that unify it all.